so some of the definitions. So there are four types of conic sections. So you could talk about them by slicing the cone or by their kind of definition. So if I said the set of points such that the sum of the distances from two distinct points, which is foci, is constant, which conic section am I talking about? So a set of points, and it's the sum of the distances from two foci. Who knows which conic I'm talking about? So let's see, there are four definitions, and I think one is a definition and four is a definition, and we're missing the other two definitions. So 1 and 4 are definitions. One is referring to an ellipse. So you've got two foci and you're stretching that string around the outside so the sum stays constant. Number 4 is referring to what? If you're equidistant from a fixed line and a fixed point, the fixed line is the directrix and the fixed point is the focus. So that's talking about a parabola. So the two definitions that I skipped on here, hyperbola would basically be definition number 1, but with the word difference. So it's the difference that's constant and it forms those two upside down parabolas. And then the one definition that I didn't use on here, the fourth one, is the circle. So that's a set of points that are all equidistant from a center point. So just kind of knowing those four definitions is good to know. The name of the fixed points is foci, we already said. And the longer segment joining two vertices of an ellipse is the major axis. So remember, in an ellipse, you have major and minor, longer and shorter. In a hyperbola, they change the name a little bit to transverse and conjugate because the transverse axis is the more important axis. It's what comes first in the equation, but it's not always the longest. So they reserve the word major because it's the longer axis, and they change the names in hyperbolas to transverse and conjugate. In a parabola, the name of the fixed line is the directrix. So just some math vocabulary about conics. I'm not going to ask you a bunch of definitions on your performance task, but it just, if I'm talking about an ellipse, I might give you information like the major axis is this long, or the foci is located here. So you need to know some of the definitions. Eccentricity is going to be on your performance task because that's an application of ellipses. So eccentricity is how oval it is. Is it a really narrow oval or is it really close to a circle? So we're going to talk about eccentricity. The length of the minor axis. So the distances are 2a for the major axis and 2b for the minor axis, because b is the distance from the center to the vertex. So the total length would be 2 times b. And then the axis of the hyperbola containing the vertices, remember that more important axis is called the transverse axis. So just kind of good to know in our talking about these conic sections. All right, so then I start to ask you some questions, kind of like one-off questions about some of the different conics. So the first one is a center. So that tells you that this is either actually it could be any of them. It could be a circle, an ellipse, or a hyperbola and still have a center. So how, by looking at the equation, can I tell which conic I'm talking about? Who can tell me by looking at number 9, what conic is this? And how do you know? Yeah, Eve, how do you know it's an ellipse? It's over two numbers and there's a plus sign. So plus would be for ellipse, minus would be for hyperbola. How do I find the center? The same way I do for circles. So this is going right 3 because it's x minus 3, and it's not going up or down at all. So the center would have to be at 3, 0. And hopefully center is something that you can find very easily because you've done it the same way for all of the conics. Equation of the directrix of the parabola. This would be more of a bonus question for your performance task. I'm not going to focus on parabolas, but first of all, if it's y squared, that tells you that it's going to open sideways, right? X squared opens up or down, y squared opens sideways. I can tell it's a parabola because x is not squared. There's only one number that's squared. And to put it in standard form, you first need to have a p-value factored out. So this is really 8 times x plus 6. The 8 is the p-value, 4 p-value. It tells you how far away your directrix and your focus is going to be. It tells you the length of your focal width. So to do the directrix, you need to do a little bit of work. First, you have to find the vertex of this parabola, which is left 6, up or down 0. Whatever is with x is left or right, and whatever with y is up or down. So I know that my vertex is at -6. So there's my vertex of my parabola. And if the 4 p-value is 8, so 4p is 8, p by itself is 2. So you have to divide this coefficient by 4. P is positive. So that tells me that my parabola is going to open to the right. So if it's left or right, if it's positive, it opens to the right. That tells me my directrix is 2 units away from the vertex, so it's behind it. So the directrix would be here at -8, right? Because if this is -6, 2 units behind it would be at -8, and they want the equation of that vertical line. So it would be x equals -8. So there's a lot in that, finding the center or vertex, figuring out which way it opens, finding the directrix. So more of a bonus question. You already know how to graph a parabola in, vertex and standard form. This is just another, hey, there could be sideways parabolas that aren't functions, and this is how you'd write them. Number 11, finding the radius of a circle. Your first step would be to complete the square. So let's go through completing the square together in case that's something that you had trouble with. One thing that you could do on this problem, because there's a coefficient of 2 in front of the x and the y, and everything else is divisible by 2, you might want to start by dividing the whole equation by 2. It would make your life a whole lot easier. For ellipses, you can't do this. You have to factor it out first. But we could divide everything by 2, right? So we'd get x squared plus y squared minus 2x plus 6y minus 9 equals 0 as our first step, dividing everything by 2. And then your next step is to group all your like terms together. So the x squared and the -2x go together. The y squared and the 6y go together. Oops, you can't see this. And then I'm going to move the 9 to the other side. So you leave room to complete the square and you leave room to complete the square. And do you remember how to complete the square? What the formula is? What do I do, Jack? Divide this number by 2 and square it. So -2 becomes -1. And then when I square -1, I'd get +1 that I add to both sides of the equation. And then this would be 6. So 3 squared is 9. I have to add 9 to both sides of the equation. And then once I have these completed squares, I can write them in factored form because they're perfect square trinomials. So this would be x minus 1 squared plus y plus 3 squared equals a total of, what's this, 19? So here's my equation. So now they want me to state the radius. So how do I find the radius from a circle equation? 19 is r squared. So I'm going to take the square root of 19. So I could either say it's just the square root of 19, or I could actually find the decimal. You could leave your answer either way. Square root of 19 is about 4.36. But either answer is correct because that's the exact radius. If you were graphing it, you'd probably need to estimate 4.4. Does completing the square seem familiar? You've done it enough that you could get there, you think? If you need help on completing the square, make sure to ask for some help. All right. Number 12 is again an ellipse because of the plus sign. So to locate the foci, let's talk about how to locate the foci of an ellipse. The first thing would be, let's just figure out what this ellipse even looks like, maybe by sketching a graph. Would it be easier if you had a piece of graph paper to actually graph it, maybe? Let me get you a piece of graph paper. Just so then you can count off tick marks and where the center is. All right. Hopefully it'll fit on this graph, this board here. I'm gonna need dry erase markers. That might be tricky too. Oops, I'm gonna pause this so it's not. The first thing you would do is identify your center. So right 2, down 4, right? So you're gonna plot your center of your ellipse. All right, so right 2, down 4. 1, 2, 3, 4, right? Is the center. And then let's see, we have to go 6 in either direction horizontally. So 1, 2, 3, 4, 5, 6, put a dot. 1, 2, 3, 4, 5, 6, put a dot. And then up and down 3. 1, 2, 3. 1, 2, 3. So there's my horizontal ellipse, right? I can tell it's horizontal because in the original equation, the larger value 36 is under the x, and the 3, or 9, but b would be 3, is under the y value. So here's the general, what it's going to look like. The foci are going to be somewhere on this major axis. So we need to figure out from the center how far away would each of the foci be located. So the equation that you need is the Pythagorean identity that a squared always equals b squared plus c squared for an ellipse, because we need to find c. So either to locate the foci or calculate the eccentricity, you need to figure out c. So for our equation, a squared is 36, b squared is 9, so 36 equals 9 plus c squared. So we would subtract 9 to the other side and then take the square root. So it ends up being the square root of 27, right? 36 minus 9 is 27. So if c squared is 27, c is, I actually have to round it because I'm going to graph it. Let's see, 5.2. So if I go 5.2 away from the center, 1, 2, 3, 4, 5.2. This is a pretty oval ellipse. 1, 2, 3, 4, 5.2. Because the foci are pretty close to the endpoints of that axis, right? So they want to actually locate those foci. So when you're looking at it, the y value stays the same as the center, and the x value is going to be x plus or minus that square root of 27, right, to get to either foci. So the way I would write the coordinates would be, The center was at 2, and then I'm going to go plus or minus the square root of 27, comma, -4. So I'm representing my y value for both of the coordinates with -4, and then the center was at 2, and I would just add or subtract the square root of 27, or if you actually want to add or subtract 5.2, you could do it that way, or reduce it. What would that be? 3√3 if you reduced the square root of 27? Any of those coordinates would be fine. So if you wanted to call it 7.2, right, this is 7.2 comma -4, you could write it that way too. 7.2 comma -4, and then this one would be whatever. We're starting at 2 and we're subtracting 5.2, right? So -3.2, -4. So to me, finding the foci of an ellipse, I think, is a little bit challenging. Okay, so number 13, I'd like to do together because we need to put an ellipse equation in standard form by completing the square. So I think what we'll do is we'll finish to the end of number 14, and then we might take a walk around the block, either outside or inside, for a few minutes, and then come back and do the graphs together. And then you've got the review sheet, that second page that I'd like you to complete on your own, either in class or for some homework. All right. Oh, we got to do equations of asymptotes. Okay, so eccentricity, number 13. Oh, look what I just found in here. Good one. All right, so for 13, you can't just go through and divide by 16 this time, right? Because I can't divide 25 by 16. That's not going to work. So your first step would be, let's just get our like terms together. So I'd put 16x squared minus 96x first. And then 25y squared minus 200y second. And then equals -144 last. You with me on that step? So I've grouped together my like things and I moved the 144 to the other side. So now individually, I'm going to factor out the greatest common factor. So I have to factor out, what is 96 divided by 16? It is 6. So this is really 16 times parentheses, x squared minus 6x, and then close parentheses. So I take 96, divide by 16, and this is my new trinomial inside here. And then here, I'm going to take out a 25, and I'll have y squared minus 8y here. Because 200 divided by 25 would be 8. So it complicates it a little bit to have an ellipse. You complete the square inside this parenthesis right here. So you ignore the 16 for a minute. So half of -6 is -3, and then you square it to get 9. But when I write plus 9 here, I'm not going to write plus 9 on the other side. I actually have to do 16 times 9 because I would distribute to get the full value. So 16 times 9 is actually 144. So I'm actually adding 144 to the other side to balance the equation. And then on this one, -8, I'd be -4, and then 4 squared is 16. So I'm adding 16 inside this trinomial, but I have to add 25 times 16 to the other side. And sometimes people forget to distribute and add. So I'm really adding 400 to the other side of the equation. So I actually have a total of 400 because -144, +144 adds up to 0. So I have 400 over there. So I have 16x minus 3 squared plus 25y minus 4 squared equals 400. And the last step for an ellipse is you have to get 1 on the other side. So to finish for an ellipse, you have to divide through by 400 to get it in standard form. So 16 over 400 would reduce to what? 400 divided by 16 is 25. So x minus 3 squared over 25. Sorry, I didn't give you much room on your paper, I'm realizing. Plus y minus 4 squared over 400 divided by 25 is 16 equals 1. So if you didn't have enough room to follow along, if you just want to write down this equation, this is the equation for number 13 that we have to figure out the eccentricity. So we're going to use that same equation, a squared equals b squared plus c squared. I know a squared, 25, the bigger number. I know b squared, 16. So this must be a Pythagorean triple, right? Because 16 plus 9 is 25. So c by itself is 3. A by itself is 5. Eccentricity is c divided by a. So 3/5, which is what? Isn't that 0.6? So the eccentricity is 3/5 or 0.6. If it was 0.8 or 0.9, now you're getting really elliptical. And if it was like 0.1, it's really circular. So it's somewhere between 0 and 1. You can never be 1 because you'd be a flat line. You could be 0. If you have an eccentricity of 0, you are a circle. All right, so the last one before we stretch our legs, 14, and then we'll come back and do the graphs. Equations of the asymptotes. Let's think about how to graph the hyperbola. Do you want to graph it on that that board? Do you want me to give you maybe a paper towel you can wipe off your circle to practice graphing the hyperbola before you have to do another round on the next page? So you already raised yours. You need a towel and erase it. I just keep getting the rubber all over my fingers. Okay, so we were going to graph this hyperbola. Try to get this up a little bit higher. Let's see. Oh yeah. All right, so what am I graphing here? I'm graphing, it's in Conics form. The y goes first in the equation. So the y is first, telling me that it's going to be a vertical hyperbola. My center, I find it is 4, -2, right 4, down 2. So 4, -2 is the center of my hyperbola. And then in the vertical direction, I'm going to go 2. And in the horizontal direction, I'm going to go 3 because I take the square root of a squared and b squared. So vertically, I'm going to go up 2, put a dot, down 2, put a dot. I like to just write down that those are going to be my vertices so that I remember it's a vertical hyperbola. And then I'm going to go left or right 3. And those are going to be the endpoints of my conjugate axis. And then you box in the shape. So if this were an ellipse, you would just draw the ellipse. But because it's a minus sign, it's a hyperbola shape. And what you do is instead of circling the ellipse, you box in this rectangle. The rectangle helps you draw in the asymptotes of your hyperbola. So the diagonals of the rectangle become the asymptotes of your hyperbola. And then up here where I wrote vertex, that's going to be where my hyperbola goes. So my hyperbola is a parabola shape that hits the vertex and then swings out towards the asymptotes. So if you haven't done 407 notes, it kind of goes through how to graph a hyperbola. So just kind of the big ideas, you know, that it's very similar to an ellipse, but you box it in, do the diagonals, and then they go in other opposite directions. So they want the equations of these asymptotes. So it's hard to write them because we don't know the y-intercept. So I know the slope is 2/3, right? Up 2/3 or down 2/3. I know the slope, but it's hard to figure out these y-intercepts. So what you can do is use point slope form. Point slope form requires one point on the line. Isn't the center of the hyperbola on both of those lines? So to write it in point slope form, it's going to be y plus 2 equals plus or minus the slope of 2/3 x minus 4. The y plus 2 is coming from where the center is. The x minus 4 is coming from where the center is. Point slope form is just y minus y1 equals the slope x minus x1. So all I'm doing is substituting in the slope and substituting in the coordinate of the center, and voila, I've got the equations for my asymptotes. Again, hyperbola equations of asymptotes would be more of a bonus for the performance task, but at least by reviewing how to graph a hyperbola, we can see how the equation fits together.